Hey guys, today we will be going into probability models. So this is more ways that you can model situations based on random chance in the real world. So the two main types that we will be going into today can only be used for a certain type of scenario. So it can only be used when the scenario can be classified as a Bernoulli trial. So the conditions for some situation to classify as a Bernoulli trial is when there's only two possible outcomes, so success and failure. The way you can think of this is like you choose one event to be your success and then everything else becomes a failure. So if you're rolling a six-sided die, this doesn't make it not a Bernoulli trial as long as you choose one specific event as your success. So if you choose rolling a 5 as your success, then rolling a 1, 2, 3, 4, and 6 becomes your failure. So you have two possible outcomes now, either a success or a failure. It's just that each one contains a different amount of stuff. Next, you have that the probability of the success, which we call P, is the same for each trial. So if we're rolling the die, if we want to roll a 5, then the probability of rolling a 5 will be 1 out of 6 each time because the dice has 6 sides. Next, we have to satisfy the condition of independence, so each trial must be independent from the other. The outcome of one trial cannot affect the outcome of another trial. And then finally, we have to sample under 10% of the population. So this last condition does sound a little bit weird, but it's meant to ensure that each trial remains independent. The way you can model this is you can think of a bag of M&Ms, and then if inside the bag of M&Ms there are 10 M&Ms, and 2 of them are orange, then the probability when you draw an M&M out is 2 out of 10, right? But when you take one M&M out and eat it, let's say it was a green M&M. So inside there's still 2 orange ones, but there's 9 left over. So now the probability of getting an orange M&M has changed from 2 out of 10 to 2 out of 9 because you have eaten a non-orange M&M. What this essentially proves is that if you sample too much of the population, you are bound to lose independence because the probability is going to shift by some significant value. So our first type of model is called a geometric model. So once our scenario has satisfied the condition of a Bernoulli trial, then we can choose to use a geometric model to represent the scenario. So the main point of a geometric model is that it is waiting for success. So one way you could think about these problems is how many people should we expect to test before we find someone with type O blood? So here we see we're waiting for someone with type O blood to walk in. So we're waiting for our success, so type O, to happen. So here the main characteristic is that there's no fixed number of trials and you're just waiting for a success to occur. The main thing you'll be solving for here is the number of trials until your first success. Important numbers you need to know here are your P, so that is your probability of success. Your Q is your probability of failure, and these two are really interrelated because, as you know, all probabilities add up to 1, right? So if your probability of success is P and everything else is failure, then your Q is equal to 1 minus P. So always, if you're given your P, you already know your Q. It's just 1 minus P. So this notation might seem a little bit weird. The big X is our random variable, and our small x is the number of trials that we're going to wait for. So if we're rolling a die, and then we want to know the probability that it takes 6 rolls to roll a 5, then we would write it as P of x is equal to 6. So we would read this as the probability that we need to run our random situation 6 times before getting a success. So the probability we have to roll our die 6 times before getting a 5. So that is equal to our P, so the probability of success, times Q to the power of our small x minus 1. In this case, our small x is a 6, right? So then it would be Q to the power of x minus 1, so 5. We have our E of x again. This is our expected value, so how many times we expect to roll the die before getting that 5. So we can also notate this with a mu, the Greek letter mu, and it is equal to 1 over P. So if the probability of rolling a 5 on a die is 1 over 6, then 1 over P is equal to 1 over 6. So we would expect to roll our die 6 times. And finally, we have the standard deviation of the number of times we will need to roll the die. So that can be notated with a sigma, and it is equal to the square root of q, so our probability of failure, over our probability of success squared. Putting that into practice, we have a problem here. So a company claims that 10% of their cereal boxes have a toy inside. How many boxes would you expect to open before getting a toy? And what is the probability that we get a toy in exactly 5 tries? So there's 2 different problems here. The first one is how many boxes you would expect to open. So you see the word expect here, and you immediately know you have to use your formula for your mean. So how do we find that? Well, the first thing you do is list out all of your important numbers. So we need our p. So our p is our probability of success. Our success here is defined as getting a toy. That's what we're looking for. And we know that the probability of that is 10%, as the company claims. So p is equal to 0.1. And we know our q too, because our q is 1 minus p. So q is equal to 1 minus 0.1, which is equal to 0.9. So there's 2 main questions here. The first one is asking how many boxes you expect to open before getting a toy. So that is our expected value formula that we have up here. So 1 over p will give us our mu. So again, writing down our formula, e of x, which can also be written as mu, is equal to 1 over the probability of success, which we have written out here, 0.1. So substituting everything in, we get that mu is equal to 1 over 0.1, which is equal to 10. So we expect to open 10 boxes before getting a cereal box with a toy inside. Our next question is asking the probability that we get a toy in exactly 5 tries. So we open box number 1, there's no toy. We open box number 2, there's no toy. We open box 3 and 4, and there's still no toys. But on our 5th box, we get a toy. So what is the probability that this occurs? So writing that out in probability notation, that looks like p of x, so that is our random variable, is equal to 5. So it takes 5 tries to get a success, so get a toy. That is equal to p times q to the power of little x minus 1. Because this probability accounts for our success on the 5th try, and this one accounts for all of the failures before it. So what is the probability that we failed on all of the tries before our first success, and then what is the probability of getting that success on the 5th round? So doing the math, we end up getting 0.1 times q, so 0.9 to the power of little x, which is 5, minus 1, which is 4. Putting that into a calculator, we get 0.06561. So there is a 6.561% chance that we get our first success, so we get our first toy on our 5th box. Combinations is basically how many different ways you can arrange a situation. So let's say you have a classroom of 20 students and you want to pick out 4 to represent the class in the student council. Your combinations would be how many different ways you can take out unique groups of 4 students at a time. So this could be students A, B, C, and D, that would be one combination, or A, B, C, and E, etc., until we get all the different combinations. Note that order here does not matter, because combinations just asks for a unique group. It doesn't matter the order that it comes in. So the way it's notated, there are 3 main ways that we use. The first one is up here. You have your big C, and then you have an N here and an R value. So your N is the total number of people in your situation. So this is the big group of people that you're choosing from. In our classroom, that would be our total of 20 students. So N is your total number that you're choosing from. Your R is the size of the group that you're making. So we wanted 4 students for the student council. So our R for that situation would be 4. And therefore it would be read as 20. We read our N first. 20 choose 4. That's written out here, N choose R. And the formula for this is N factorial. So in our situation, 20 factorial over R factorial. So 4 factorial times N minus R factorial. So 20 minus 4, which is equal to 16 factorial. A lot of calculators do have functions where you can just put in your 20 and your 4 and get out a number and you won't use this formula at all, but this is still good to know in case you need to calculate it by hand. Another common way of writing out combinations is this way. This is the way that I put it into my own calculator. NCR is the name of the function, and then you put in your numbers n and r as your parameters. And the one that I use the most in handwriting would be this one. So you have your n and your r as a sort of matrix looking thing. So you put your n, your total number, on top, and then your r, the number you're choosing, at the bottom. So this is used in a binomial model. In a binomial model, the main difference that sets it apart from a geometric model is that in a binomial model, you are counting the number of successes that you have gotten. So here you have a set number of trials. You know how many trials you're going to run this time, but you want to know out of all those trials you ran, how many were a success. One way you could word this in a real life situation would be, out of 50 people tested, how many people do we expect to have type O blood? So we see a set number of trials, we have 50 people, and then we want to know how many successes there were. In a geometric model, there was only one success, and that was our stopping point. The place where the success was dictated how many trials there were, and it was not a set number for every situation. So for a geometric model, it's when does the first success appear? For a binomial model, it's out of this many trials, how many successes did we get? Our P and Q are still the same. We have our probability of success as P and our probability of failure as Q, which is equal to 1 minus P again. We have a new number here, which is N. N is our total number of trials. So how many trials are we going to look at in our binomial model and count successes from? Now we have this notation again, so the probability that big X is equal to little x. Here, it's a little bit different in terms of what it represents. Our big X doesn't represent the number of trials we wait for anymore. This now represents the number of successes we got. So the probability that the number of successes we got out of n trials is equal to X. So in our case with the blood testing, we could say if we had 50 people that we tested and we want to know the probability that 10 of them have type O blood, then we would write that as P of the number of successes is equal to 10. So this is equal to the combinations of n choose r. So out of our 50 people, how many ways can we get 10 people out from there? So how many unique groups of 10 can we pull from those 50 people? And then times the probability of success to the power of little x, so 10, and then the probability of failure, q, to the power of n minus x, so all the remaining trials. Breaking this down into something that's not just letters and numbers, going back to our blood testing example, if we want to know the probability that 10 people have type O blood out of the 50 people, then putting that out, if we have a group of 10 here that all have type O blood, that means that the remaining group of 40 has not type O blood. So if the probability of someone having type O blood is 30%, I'm pulling this out of my butt, I don't know the actual numbers, then first we have to account for every single person having some certain type of blood, right? So P to the power of X is basically just the probability that exactly 10 people have type O blood. So it would be 0.3 times 0.3 times 0.3 for 10 people. And this shows our group of 10 having type O blood. Now, we have to account for the remaining people not having type O blood. So that's where our Q to the power of n minus x comes from. This n minus x just means everyone that does not have type O blood, everyone that is not a success. So that would be 0.7 times 0.7 for 40 terms because there are 40 people left in the trials. So that is where our P and Q terms come from. Our n choose r is made to account for every possible way that we can choose groups of 10 to have type O blood. Because what we did here with the P and Q only accounts for one case. However, we need to account for the other ways that people can be arranged and still have 10 people with type O blood. For example, the first 10 people that walk in could have type O blood, or the last 10 people could have type O blood. There's so many different ways that you can arrange this, and that's what the combinations takes care of. It expands the probability to account for all the different ways that this could happen. Finally, we have our expected value, so our e of x, which is equal to mu. That is a pretty simple term. It's just equal to n times p. So number of trials times the probability of success. Our standard deviation, still denoted by sigma, is equal to the square root of n times p times q. Putting this into practice, we have a problem similar to the one we did earlier. So a company claims that 10% of all of their cereal boxes have a toy inside. If you open 12 cereal boxes, how many toys will you get on average, and what is the probability that you get 3 toys? Again, there's 2 different problems here, but we'll go into that in a minute. First, we need our important numbers, so p, q, and n. So what is our p? First, to decide what our p is, we need to know what our success is. Our success appears to be getting a toy. So what is the probability that we get a toy? That is 10%, so again, our p is 0.1. And that makes our q 0.9, because q is equal to 1 minus p. Now our n is the number of trials we're going to run. So that's how many cereal boxes we're going to open and count how many toys we get. So that would be our 12 cereal boxes. The problem said that we're going to open 12, so that is our n. Now we can answer the questions. How many toys will we get on average? You see the on average, and that tells you that you're calculating expected value. So your e of x, or mu, for a binomial model is equal to n times p. So what is our n? That is 12 times our p of 0.1. So that is equal to 1.2 toys. So it sounds kind of weird, right? A decimal number of toys, but because it says on average, then a decimal number of toys is fine. Because what this means is basically if I open 12 cereal boxes, I'm going to get, let's say, 2 toys. But if you open 12 cereal boxes, you're going to get a different number, right? If I open 12 boxes, you open 12 boxes, and then a bunch of other people all open 12 boxes each, if we average up the number of toys that each person gets between all of us that open 12 boxes, we will get around 1.2 toys. So that's the first question. The second one says, what is the probability that you get 3 toys? So that would be the probability that x, number of successes, is equal to 3. So that's our big complicated formula again. So first, we have to account for all the different ways that we could get 3 toys. It could be the first 3 boxes, the last 3 boxes, the first, second, and fourth box, I don't know. So that would be 12 boxes, choose 3, times p to the power of little x, so p to the power of 3, times q to the power of n minus x, which is equal to 12 minus 3. Plugging all of our numbers now, we get 12, choose 3, times 0.1 to the power of 3 times 0.9 to the power of 9. Normally you can just plug this directly into the calculator, but for the sake of demonstrating combinations, I'll multiply out the whole thing. So the formula for combinations is again our big factorial thing. So we have our n factorial over r factorial, so that's our 3, times 12 minus 3 factorial, which is equal to 9 factorial. And then we have our 0.1 to the power of 3 here and 0.9 to the power of 9. Here we can cancel out a bunch of stuff. 12 factorial is equal to 12 times 11 times 10 times 9 factorial. So we can cancel these out. 12 times 11 times 10. And then 3 factorial is equal to 6. So we can cancel that out of the 12. And we have a remaining 220 times whatever this is. Putting that into the calculator, we get 0.0852. So there is approximately an 8.52% chance that we will get 3 toys when we open 12 cereal boxes. So the last thing you really need to know is how to determine when a situation is a binomial model, a geometric model, or neither. A situation will be neither when it doesn't comply with the conditions of the Bernoulli trials. So here are 3 different situations. I'll tell you right away. One is binomial, one is geometric, and one is neither. So the first one says going fishing and counting how many minutes until we get our first fish. First and foremost, we can see we're counting how many minutes, so we don't know how many minutes we're going to fish for. So that tells us that this is likely going to be a geometric model because we don't know how many trials we're going to run, we don't know how many minutes we're going to wait for, where the minutes are our trials. And this doesn't seem to violate any of the Bernoulli trial conditions, so we can just put that this one is geometric. Next, seeing how many houses out of one neighborhood have a pool. This one is a little bit tricky at first because there's no set number that's written in the problem, right? But you will notice that it says one neighborhood. One neighborhood does have a set number of houses. The problem doesn't tell you how many houses, but you should know that there is a specific number of houses in the neighborhood. So this one is binomial. Now the last question, because I know I said one is geometric, one is binomial, that means the last one's neither, but I'll explain why. So it says drawing from a deck of cards to see how many cards you need to pick before drawing a face card. There are about 52 cards in your standard deck of cards, and there is a condition in the Bernoulli trial conditions that says that you cannot sample above 10% of a population. Going back to our cards, 10% out of the 52 cards would be 5.2 cards. So in order to not violate our conditions, we can't choose more than 5 cards until we draw a face card. The probability of us having to choose more than 5 cards as we try to find a face card is actually quite large considering how few face cards are in relation to the rest of the deck, which makes it really likely that we'll end up violating our independence, because once we go over 10% of all of the cards, the probability of getting a face card begins to change. So these are the calculator functions you really need for this unit. I will go really in detail with how to find these and how the exact notation for these works in my calculator video, but the main kinds of situations you would use these in is the geometric CDF and binomial CDF are used each for their respective probability models. Geom CDF is for geometric model, binom CDF is for binomial models, and it's for your more complicated probability questions. So in the questions we've done, it's just said something like, what is the probability that we get a fish after 15 minutes or something like that? Or what is the probability that we get a toy on our 5th box? We only have to calculate the probability of getting a toy on box number 5. But if we ask for multiple boxes, so if we ask what is the probability that we get a toy after opening between 7 and 10 boxes, you can calculate this by hand by just adding up the probability of getting it on your 7th box plus the probability of getting it on your 8th box, etc. That would be a bit time consuming, but it's still doable. However, this does make it a lot more convenient, and there are some questions that you can't do by hand. For example, if I ask you, what is the probability that you get a toy after opening at least 5 boxes? At least 5 boxes means you have to add up all of the probabilities from 5 to infinity. This is not something you can do by hand, and this is something that you have to do with your calculator. So this one just calculates for you what is the probability that you get your first success between X and Y tries. Your binom CDF is a little bit similar. It basically says, out of n trials, what is the probability that we get between A and B number of successes? So if we open 400 boxes, what is the probability that we get between 2 and 344 successes? This would be really tiring to calculate by hand, and I doubt you have the time nor patience to do that, so this is what binomial CDF allows you to do. If you're interested, go watch my calculator video. And yeah, that's it for today, so thanks for watching. I hope you learned something. Peace.